your example, something might be turned around a bit. It could be switched around, but I think the general setup should be the same. So this is number 15 from section 2.1. Alrighty, so they are saying, suppose you're, oh, okay, I know what problem this one is. So they are saying, let's see if I can make this guy bigger a little bit so you can see. So this one you can see is not being defined with numbers. They're actually telling you the universal set is, the cardinal number. So they're telling you how many elements the universal set has, and instead of giving you a number, they're telling you the universal set has W elements. So W could be any number, we're just not sure what it is. They're telling us set A has a cardinal number of X, set B has a cardinal number of Y, and when you take A union B, that has a cardinal number of Z. So here they're asking you, okay, I'm not sure what these are. Okay, I think it was trying to show us the answer, but we don't want that. So let's go back down to number 15. Okay, so they want to know, why must X be less than or equal to Z? So X is right over here, which is the cardinal number of A, and Z is the cardinal number of the union between A and B. So they're just asking us, why should X be less than or equal to Z? And so basically the idea is, if you think about combining two sets, A and B, together as a union, then basically the idea is, if B has more than one element, or even has one element, right? That means A union B is going to be a set larger than just set A by itself. Because imagine, and you can try this with numbers, if it helps you out better. So we can say, okay, let's set A be, 0, 1, 2 as its set element. So that means the cardinal number for A would be 3. If set B is defined as, I don't know, let's say 0 and 3. That means the cardinal number for B would be 2. So when I talk about A union B, whatever is repeating, we would only write that down once. And then let's see that. So that would be 0 between the two sets. And then you've got 1, 2, and 3. So you can see the cardinal number for A union B comes out to be 4. So this is one scenario where you can see the cardinal number for A is less than the cardinal number for B. The other scenario could be where set B only has one element, and let's say that element is 0, which means the cardinal number for B would be 1, because you only have one element in there, right? So that means when you did A union B, since 0 is repeating between set A and set B, again, you would only write that down once, and then would bring down the 1 and 2. And you can see the cardinal number for A union B comes out to be 3, which is the same as the cardinal number for set A. So that's why they're basically saying the cardinal number X can be less than or equal to Z. So why does this happen? And that is because we can say that A is a subset of A union B. It can be an improper subset, or it can be a proper subset, just depending on that. So that's what they're basically asking you, is just to give a reason why the cardinal number for set A would be less than or equal to the cardinal number of set A union B. So like I said, just use a couple numbers, put it into your set to kind of figure out what the answer would come out to be. Does that make sense, guys? Yeah, okay. Part B of this problem is asking us, if A is not equal to U, which means they have different elements, right? They are not equal to each other. B is also not equal to the universal set. So they are asking us to fill in the blank with the most appropriate symbol, and your symbols over here are less than, greater than, less than, equal to, greater than, equal to. So we're basically saying the two sets are not equal. So, again, if we just use these two as our definition for sets A and B, and we can say, okay, the universal set is 0, 1, 2, 3, I don't know, 4 and 5. So if you think about it that way, what symbols would you use between set the value W, which is the cardinal number for the universal set, and Z, which is the cardinal number for the union between A and B?
Maybe
Less than,
equal to? Oh,
less
sorry.
than, equal to?
I think W has to be greater than or equal to.
You think W has to be greater than? Because we're basically again saying A is not equal to U, B is not equal to U. And so the idea is between union of A and B and the universal set, yeah, there's a potential that the universal set is going to be larger than set A and set B. So it should be that the cardinal number for universal has to be larger than or possibly equal to your union between A and B, because again, we don't really have the definitions to help us out. What do you think between W and Y? So again, W is for the universal set, Y is for set B.
Y is less than W.
Okay, Y should be less than W, because again, if you think about B being a subset of the universal set, then that means Y has to be less than W. So, again, when you're using these inequality symbols, remember the smaller end or the pointed side faces the set which will be smaller, the number which will be smaller. Okay, between Y and Z, so Y is for set B, and Z is again for set union between A and B. So will Y be less than, greater than, less than, equal to, greater than, equal to?
Less than?
Less than? What about less than, equal to?
Yes, but I don't know why.
Okay, so again, we don't have definitions for either A, B, or the union. So, think about it. What if, this situation that we talked about over here for the part A was reversed, and in that sense, how you came up with set B, sorry, in part A, we said, the cardinal number for set A could be the same as the cardinal number between A union B. So that logic, same logic can be applied, with set B and set A union B, because, all we have to do, if you think about this, I can just reverse this, make this set B and make this set A, make this guy set A. And then you can see your cardinal numbers can still end up being same, right? So it can be less than or equal to, because again, we don't have specific definition, so we don't know what direction this will be going in. So I would say less than and equal to, because again, we don't have specific definitions. What can we say about the last one between X, which is for set A, and union, W for set universal? X and W.
X is less than W.
X is less than W. Because again, they are telling us right here on the first statement in part B that A is not equal to U, which means A does not have the same elements as U does, or U does not have all the same elements as A does. So in this case, yes, X will be less than W. Okay, so the last part, sorry, that's the Venn diagram. I guess the third part, C is asking us to find what we think the cardinal number between A intersection B is going to be. And, of course, that information is not shared with us. So how do you think we can come up with that?
This part in the Venn diagram is the part that I was really confused about.
Okay. Anybody else have an idea what we need to do here to find this cardinal number? Okay, let's go back to our handout for 2.1, because this is where you guys will actually need to use the formula for calculating cardinal numbers. Okay, not here. There we go. This formula is what you're going to have to use to come up with your intersection. The only difference is we're going to have to switch places between the intersection and the union. So you're basically going to just rewrite this formula. So when we rewrite this, it actually will become, let's see, I'm going to try and do this over here. So we're actually moving the intersection to the left-hand side. So we're moving it over here. And then here you will have the cardinal number of A plus the cardinal number of B minus, so literally we're switching places. So this guy moves over here, minus the cardinal number between A union B. So you are having to rewrite this formula. And then using that, you should be able to calculate what this guy should be. So cardinal number for A is X. Let's see, added with cardinal number of B is Y. And then you are subtracting the cardinal number of A union B, which is going to be Z. And again, since we don't have numbers, you won't actually be able to come up with a value. You're just going to come up with this expression. So X plus Y minus Z is what you're looking at for this guy. And that's the purpose of this homework problem, is to help you understand the concepts of set theory without having to depend on, always having a numerical value, because this is more of a concept question and not so much of can you perform the operations or can you do the math. This is about, do you actually understand what's going on with set theory? So that's what this problem is. And that's why they're not using numbers and just using variables, W, X, Y, Z. So that's the first part of this problem. Now let's go ahead and look at what's happening with the Venn diagram. You know what, I'm going to have to clear this out. So with the Venn diagram, they are asking you to basically fill in, what do you think the value should be here. So in this case, we just calculated our intersection, what the intersection should end up looking like. So that's, of course, going to be your X plus Y minus Z that we calculated in part Z. Now, thinking on those terms, you have the whole cardinal number for set B given to us as Y. But remember, Y is, everything that is in circle B. So Y will be a total of what's in here plus in here. So how can we modify this part over here so that we're not, counting the numbers twice?
put x plus y minus z, y minus x plus y minus z.
Okay, would you say that one more time?
Y minus x plus y minus z, but in parentheses.
Yeah, very good. Because what we have to do is we know this entire circle is y. So that means on this part, which is on the outside, it's going to be y minus, whatever you have in the middle. So very good. You will be doing y minus, and then in parentheses, x plus y minus z. So in that same format, what can we do for a over here? And a, the cardinal number is given to us as x.
Same thing as before, minus.
Exactly.
Okay, I'm so glad because I did not know what my answers were supposed to be. I'm glad that I know now that they're supposed to be small equations.
Yeah, exactly. Because again, like I said, no numbers. And then you've got one last one over here, guys, with this universal on the outside. And the cardinal number for the universal is W. But, of course, W means everything that's inside the rectangle. So what, again, how will you modify this outer portion?
I'm not exactly sure how to write that in a simple equation.
Okay,
It
so
would be you
walk me
subtract x plus y because it's the union. So it's the universe minus the union.
okay, so you are saying from the W?
Yeah. I believe I wrote w minus x plus y in parentheses.
But then wouldn't the x plus y, because you're taking circle A as x, right? And circle B as y. But then aren't we having a little bit of the overlap because you have some common, or at least we're thinking there's going to be common elements between the two?
Well, the union is both circle A and B.
W minus z?
W minus z?
Or yeah. Yes.
I just saw that. I'm like, oh my gosh, I got it.
Yes, that is correct.
Now the question is, will it let us check our answer here? Does it give me, I guess it says submit for testing, so let's try it out. Okay, I guess
My submission says this is good.
it says this is good.
Yeah.
Okay, I guess
Alright,
that's
thank
a
you.
positive sign, isn't it?
Yes, thank you so much.
Yeah, not a problem. And just one other thing I wanted to point out over here, guys, even though we left our, equations in circles A and B as is, and it sounds like what Logan said, it will accept it, but these equations can actually be simplified. And I don't know if that's going to be an issue, because if you will see, there's two x variables here, and there's two y variables here. If you just distribute that negative sign, you end up getting x minus y plus z. So your x's actually cancel out, giving you z minus y for this blank space over here. Same thing happens here. If you again distribute that negative, you get minus x minus y plus z. Your y's cancel out, and this guy ends up becoming z minus x. And if you really think about it, it makes sense, because we are basically saying z is the union between A and B. And if you remove everything, so basically we're saying from A union B, if you remove set A, you're left with set B, which is giving us this area over here. And then the second side is saying from A union B, if we remove Y, which is actually your set B, you're left behind with set A, which is going to be this section. So they're actually just cleaning up these equations. But like I said, it sounds like if Logan got it correctly, then they don't care about simplifying this, but that would be another approach to kind of think about these two, separate areas without the intersection in the middle. All righty, good
Right.
job, guys. So anybody have question on this example over here? And
Not
this,
this.
okay. And this was number 15, and I think you said 19 you were also having trouble on?
Yeah, I'm not exactly sure what I'm supposed to put as an answer for that either.
Okay, so again, this one is based on cardinal numbers. You can see over here. So let's take a look at this. Universal is basically X such that X is the name of one of the months in a year. Let me get my pen going over here. So basically, if you think about it, if they're saying X is the name of one of the months in a year, what do you think that universal set, what those elements will be in the universal set? Because if they're saying it's one of the months, technically it means you should have all 12 months in there, right? So everything going from January, February, March, all the way to, November, December. So that's your universal set. Then they are saying for set J is X such that X is in the universal set. So, X will be part of the universal set, but also X begins with the letter J. So can you think about what months will be included in this set?
January, June, and July.
Very good. January, June, and July. Set Y, they're saying X such that X is again part of the universal set, and X ends with the letter Y. So again, what months end with the letter Y?
January, February, May, July. That's all right.
Is that all? Yeah, there you go. So now can you tell me when you do an intersection between set J, sorry, not intersection, union between set J and Y, what will you have in there?
Okay, this is all coming together. January,
Yeah.
July.
Okay, so this is union.
Oh wait, union. January, February, May, June, July.
There you go. Put everybody in the pool.
Okay, this is great.
And so what's your cardinal number here?
Okay, 5.
There you go.
Okay, thank you.
So yeah, some of these may seem abstract in a way because they're not giving you, the actual definition of the set. But if you really just read the instructions and break it down, you will see a lot of information is available. Now, I know number 15 is a little bit different because, you almost, like I said, it's a more of a conceptual problem because you have to think about the concepts and not so much about can you do the math. So that number 15 can take a little bit of, practice coming up with that. But you will see, all of these other examples that are following, they are giving you numbers, but you are actually going to be doing a lot of the similar calculation that you did over here, but now you're just working with numbers on these. So Logan, that helps you out?
Yeah, definitely.
Okay, did anybody else have any questions?
Yeah, I can figure out number 26.
26. Okay, let's take a look. What is 26? Oh, okay, 26. So they are telling us A is a subset of B, and then they want to know what would A intersect B look like, and same thing in part B, but they're going with union. So A is a subset of B. So let's think about this. If they're talking about proper subset over here, and just to kind of again familiarize you with that symbolism. Oh, where did we have that? Okay, I think it's right here in this paragraph. So they are saying, notice the similarities between our symbols over here, comparing it to our less than equal to. So that's the same thing here. They're saying to indicate a proper subset, we use the symbol, kind of looks like a C over here. They're saying while it is acceptable to write it with this symbol with the less than equal to, basically the proper symbol is this one here, because obviously everything that's in the first set is not in the second set. So it's technically a proper subset would be where the first set has less elements than the second one. There are more elements in the second one. So if you use that same logic over here, and again, if it helps, create some basic definition so you can see, we can just put 1 and 2 in here, and we can put 1, 2, I don't know, 3 and 4 over here. So A is a proper subset of B. So if you think about when you create an intersection between these two sets, what will you end up having?
One and two.
Just 1 and 2, because this is an intersection. So only thing that's common will go in here. And you can see 1 and 2 is the same thing as set A. So technically, your intersection is going to be equal to set A. So that's what you're putting in here, is that the intersection between A and B is going to be set A. And then in that same way, if you think about union between A and B, what will we end up getting over here?
Set B.
Yeah, set B, because 1 and 2 are overlapping, and then you also bring everything that's not common, so 3 and 4, and you will see this guy is the same thing as set B. So this answer here will be set B. So again, since they're not giving you a definition, they're just telling you that set A is a proper subset of B. Just create, again, something with numbers so you can visualize it. But anytime, and this is going to be true no matter what your set A and B are defined as. So again, between the intersection, it's always going to be the smaller set, so that's set A. Between the union, it's going to be the larger set, so that's set B. Roman, does that help you out?
Yeah, it makes sense now. When I was putting it down, I think I was just typing it as like a subset, not just a cardinal number.
Okay,
I
okay.
don't know how I was doing it.
Okay, okay. Yeah, so here you're just putting literally just A and B for the two sets. All righty. Anybody else? Any questions, guys? Oops. And I mean, if you guys are still finishing up the 2.1 homework, that's fine. We'll be seeing each other again on Friday. So, obviously don't hesitate to reach out to me on Friday. And if you have any questions, we can. Just again, want to remind you guys to not fall behind. We literally have 1 or 2 examples left to talk about in section 2.2, and then we're done with 2.2. And, like I said, we're not spending too much time on 2.3, 2.4. So, try to keep up with that homework and not fall behind. Yeah, Brandon, you have a question?
Can you do 23? I need a refresher on that. I can't remember what formula to use. For some reason I can't figure it out. It's like I know there's something simple I'm missing on it.
All righty, 23. Oh, with the deck of cards.
Yeah, because it would be 13. It wants the face cards and the spades. So there'd be 13 spades, 12 face cards, but then once you minus the 3, that are already spayed, so it'd be like 22, but that says it's wrong. So that's why I'm like, what am I doing?
Okay. So they're telling us each suite contains consists of cards labeled 2 through 10, followed by Jack, Queen, King, and Ace. Okay. So yeah, they're specifically telling us here, and I know we had kind of had that discussion and we have looked at that one example. So they're telling us face cards are only Jack, Queen, and King. And then picture cards they're defining as Jack, Queen, King, and Ace. Okay. So they want to know what is going to be basically the intersection between face cards and spades. So again, with face cards, it's 3 times 4. So yeah, 12. And what did you have for spades?
It would be the 13 because they said 13 in each 4 suits.
Right. Yeah, exactly. Because by the time you go from 2 to 10 plus the picture cards, it adds up to 13. So they want to know basically what is the intersection
Oh, okay.
between
So it'd be 3.
face and diamonds. Yeah,
Yeah.
because the
Okay.
only thing would be the Jack, Queen, and King of diamonds, right? In this case, so that would be falling under the diamonds category and the face card. So yeah, this will be 3 cards here.
All right. Yeah, I just misunderstood what they were asking them.
Okay, and remember we had kind of mentioned, be careful about what word they are using. And is intersection or is union. So just remember that as you guys are going through these examples. Alrighty, very good. Okay, guys, so let's get into that last part of section 2.2. And we had looked at, I think, was example 30 our last one that we had talked about? Yeah, I think that was the one with the shading question. Alrighty, let's look at we're going to be looking at number 36. And this one is talking about if a person, first let's look at the instructions here. So for 36, they're actually asking us to use this figure 2.34. It will not let me put it all. That's actually changing our page. Okay, let's do it this way. Go back one page. So 2.34 is actually this table over here with the blood types. There we go. And this one they're saying is blood types per 100 people in the United States. So we're basically saying if you take a group of 100 people, then 38 of those would be O positive, 7 would be O negative, 34 are A positive, 6 people are A negative, 9 are B positive, 2 are B negative, 3 are A positive, and 1 person is going to be, AB positive, and 1 person is going to be AB negative. So based on this table, they're asking us these questions over here. So I guess we might have to go back and forth because it won't let me open it up over here. So the instructions are basically, complete the exercise and round off your answers to the 10th of a percent. So just keep that rounding rule in mind. They are asking us, of all the people in the United States who have type O blood, what percentage are Rh positive and what percentage are Rh negative? So that, of course, the positive and the negative they had with each blood type over here. So looking at number 36. Oh, and this is going to be the tricky part, isn't it? Let's see if we can open this guy. with, because we can at least see the type O in our little table. Okay, so here's the table you're supposed to use. And they're asking us for type O, what percentage are RH positive and what percentage are RH negative? So how would we calculate these percentages? And we had talked a little bit about last time about calculating percentages. So you're actually using the same concept over here.
Divide.
By
138 by 100. Is it O positive or just all O's?
okay, so this is not working. You know what I'm going to do? I'm actually going to go ahead and see if I can copy that table over. Okay, let's do this.
What does RH mean though?
You know, that's a very good question. Let's take a look. I honestly do not remember. I've read about it before, but it should be in that little blurb we had that I was telling you guys about. Okay, so they're talking about it's the presence or absence of a protein in the human blood, which is referred to as the RH factor. So the blood that contains the protein is labeled as positive, and the one that does not contain is labeled as the negative. But I don't think they're getting into too much detail about what the protein is. But yeah, I guess it's the name of the protein that exists in the human blood. Okay, so let's read that question once more, because as Logan was asking, is it based on the 100 or is it just based on the blood type? So this one is saying of all the people in the United States who have a blood type of blood type O, what percentage are positive and negative? So again, just reading that question, what do you guys think? Is this out of the per 100 people, or is this out of just the people who belong to this blood type?
Everyone.
Be the 100 because it says of all people.
I was
Yeah, but-
thinking we would do O positive divided by O and then O negative divided by O.
Yeah, Brandon, even though they are saying of all the people, they're actually saying of all the people who have type O blood, right? So they're specifying that from, the total people we're looking at, from those who have type O, what percentage would be RH positive and what would be RH negative. So the first thing we want to do is calculate our total for the O positive. So what will this total be between just the type O blood?
45.
45.
Yeah, 45. Very good. So that's a total of 45. Okay, I guess we don't need that. So that is going to be 38 out of 45, like Adali mentioned. So what will this percentage come out to be?
Be 0.84, so 84%, and it said we were rounding to what?
To the 10th?
To the 10th, so it'd be 80.
No, think about you're doing 10th.
Oh,
10th.
so it'd just be
84.4.
yeah.
Yeah, very nice. So you've got your raw answer as 0.8444, it keeps repeating. So when you're rounding this to a percentage, that will become 84.4%. So just, one decimal place. And using that same rule, what percentage is then negative, RH negative?
15.6%.
15.6, because again, the idea is we're only doing this with the type O blood. So out of 100%, if you subtract that 84.4, you would end up getting your 15.6%, or you could do 7 divided by 45, and it should still lead you to the same conclusion. So again, approximately this guy would come out to be 15.6%. So either subtract the percentage from 100, or just do the math all over again. And then let's see, one more example I wanted to look at, and this one, let me go ahead and save this guy, is going to be number 42 here, but this is not really based on the table. This is more of, a concept question again. So number 42, they're asking if a person has type AB blood, what blood types may a person receive in a transfusion? So basically, who can this person get, transfusion from? And this might be something you may have to kind of go back and look at that little, blurb they have over here. There we go, blood types. So that's a really neat Venn diagram to kind of show you the relationship. And here's another one.
It'd be all of them, wouldn't it?
Yeah, it would be, because the type AB blood, and you can kind of see that in this last paragraph over here. They're basically saying, for instance, type AB negative indicates the presence of both A and B molecules. With the absence, there we go, there's the name of the protein, rhesus protein. They're saying type O indicates the absence of both A and B molecules with the presence of the rhesus, and they're talking about in the Venn diagram, you can basically see that they're kind of dividing it in the positive and the negative halves, but again, you can kind of see that it's just the absence of A, B factors in them, but it basically means it will not negatively affect the person who has type AB blood, because they are able to receive that type O blood, because again, with the absence of those blood groups, come on, buddy, it will still be safe for this person to receive a transfusion from anyone. And I'm sure you guys have heard the term of, universal blood donor with the type O's, because again, they do not have a negative effect on people who have other blood types. So yeah, for number 42, they can actually receive transfusion from any type of blood, so all blood types. All right, guys, so this was just, a different type of example that I wanted to work with you, especially with the number 36 example that we did.
Question real quick.
Yeah.
So like, say this question was on the test, when it goes to writing it, would you have to do write it all out, like positive and negative, or just like, you know what I mean? Like if it didn't have an option for all, wanted you to write it all out, would you have to do A positive, A negative, AB positive?
No, you can just say that they can receive transfusion from all blood types.
Okay, just wanted to make sure it wasn't one of those weird.
I'm not sure if this is a multiple choice question or not in your homework, because a lot of times they do that. They give you multiple choice questions, so you're just able to pick the right option. So that could be something to look at. I'm not sure what this guy does.
I think it's number 17 on the homework, but it's not multiple choice.
Sorry, this is 2.1. We need 2.2. Okay, so this one, it looks like they're saying enter your answers as a comma separated list. So yeah, in this case, Brandon, then you are actually putting in the blood type.
Yeah, so would you have to put positive and negative, or could you just put, oh, it's A, B, and, B instead of all of it? Does that make sense?
Let's take a look. So just the blood type without the positive and negative.
All right, cool.
Okay, awesome. I'm glad you asked me that because yeah, sometimes they have their own way of wanting you to write your answers. Alrighty, guys. So this is your, you've got a couple examples in your handout where you can look at these types of examples if you need additional help. Alrighty, so the next section with chapter 2 is getting into counting. How do you do different types of counting? So, we're talking about the fundamental principle for counting, and then we've got our combinations and permutations. So all of these methods together are what we call as combinatorics. And, again, like I said, we're not going to be spending too much time. I just want you to get a basic understanding on how to do different types of calculations. So that way, when we actually get into chapter 3, you will see the use for these different counting techniques. So, here we're just talking about how to do the counting, and then in chapter 3, we'll be able to elaborate more. So one of the ways that we go about with the fundamental principle for counting is actually by using a tree diagram. And this actually helps us list all the choices. If you just want to know what the count is, like just a numerical value, then of course the tree diagram is not going to be helpful. The tree diagram is more for knowing, if you went with choice 1 and then you selected one of the options from choice 2, and then, keep moving forward, what you can come up with. And, some of the examples they'll talk about is like if you're at a restaurant, they will have couple different salad combinations, right? Soup combinations, and then they will have, 7 or 8 entrees with sides. So if you had to look at all the different meal options that you could get from that, how many would it be? So that would be the counting. Now, if you actually wanted to list out all the different options, and that's where the tree diagram kind of comes into play. So if you look at one of these examples over here, they're talking about if you buy 2 pairs of jeans, 3 shirts, 2 pairs of shoes, how many new outfits do you have? So in this case, if you just take the 2 pairs of jeans, multiply that with the 3 shirts, multiply that with the 2 pairs of shoes, you will basically get, what is that going to be, 12? So you have 12 new outfits depending on how you combine them. And this is where, the tree diagram comes into play. So you've got your choices between the 2 jeans, the 3 shirts, and then the 2 pairs of shoes. So you can see if you go with jeans 1, shirt 1, shoe 1, that's one combination. You can do the second jeans, shirt 1, shoe 1, and that gives you, basically the shirt and the shoe stayed the same, but you changed your jeans. You've got 2 different possible combinations for your outfit. So you can see once you use the tree diagram, you end up getting your 12 different possibilities. So as far as just coming up with how many new outfits go, we use, the fundamental counting principle over here. But if they ask you to list out all the possible outfits you're going to have, then, this is where the tree diagram kind of comes into play. So that's kind of how this fundamental principle of counting works. So let's do our own example and see if we can find something to help us out here. All right, how about we look at number 4 from our textbook. Oh, wrong section. 2.3, there we go. Okay, so number 4. You know what? instead of that, let's do number 3. So this one is talking about Jamie has decided to buy either a Mega or a Better Byte desktop computer. So those are 2 options in the computers. She also wants to buy Big Word, Word World, or Great Word, word processing software. So those are 3 options. And she wants to buy Big Number or Number World as her spreadsheet. So kind of like an Excel option. So that's 2 Excel, 2 spreadsheet softwares, 3 word processing softwares, and she's got to decide between 2 computers. So they're saying using the fundamental principle of counting, determine how many different packages of a computer and software Jamie has to choose from. So again, if you think about that, that's 2 computer options, 3 word processing, and 2 spreadsheet. So again, 3 times 2 times 2, you will see it gives her 12 different packages to choose from. So that's literally what you do with this fundamental principle of counting. You look at how many different options you have and you multiply them together. Now, as far as the tree diagram goes, we'll need to spend a little bit more time on that. So let's go ahead and move this over to our notebook here. So let's see, we've got Mega or Better Byte for the desktop computer. We've got Big Word, Word World, or Great Word. And then we've got Big Number or Number World. As your spreadsheet software. All right, Roman, I'll see you on Friday. Thank you. So the way your tree diagram is going to work over here, guys, is basically, kind of like you saw with that jeans example, and let's get rid of this other stuff here. So you start with your, starting point, and you start with the 2 computers that we have. So that's the Mega or the Better Byte. And we may have to make this actually a little bit more spread out, I think. Maybe move this guy a little bit lower. So that's the Better Byte. Okay, so if you went with Mega, then you have options of choosing 3 different word processing software. So you've got your Big Word, Word World, and you've got the Great Word. So those are the 3 word processing softwares. So those would be the same 3 options you would have to do with the Better Byte computer. So same thing, Big Word, Word World, Word. Man, I think they're doing this on purpose to create like a tongue twister. So the 3 word processing softwares, and then you've got the 2 spreadsheets. So now with each one of these, we would have to do the 2 spreadsheets. So that's your Big Number and Number World. So that's kind of how you set up your tree diagrams. And of course, this will be the same for all of these options going down. And after you come up with your table or your tree diagram, then you actually have to list out all the possible combinations that we can come up with in this case. So that would end up looking like, well, basically what they have listed over here. So then you have to come up with this list of all the possible different combinations. So, you're going with jeans 1, shirt 1, shoe 1, then you're going with jeans 1, shirt 1, shoe 2. So that takes care of that combination. Then you're still with jeans 1, shirt 2, shoe 1, jeans 1, shirt 2, shoe 2, and of course you keep moving forward. Jeans, shirt 3, shoe 1, then again shirt 3, shoe 2. So you keep coming up with all these possibilities, and that's what they're asking us to do in this part B, is list all the possible packages that we can come up with between the computer and the different software that Jamie wants to buy. So, again, you would have to repeat that same option over here with the spreadsheet software with these guys down here. So that was big number, number world, and of course, same thing going down. And you can use abbreviations to make the tree diagram if you wanted to save time. But when you start listing all your options, you definitely want to write it out all in words. And I don't know your homework if it has multiple choice or if it wants you to type. But if it wants you to type, then of course they would want you to use all the original words. So if you look at the different combinations that we can come up with, start with your mega computer. So that would be your first possibility, is mega. And then that would be going with the first software. So that's big word. And then going with the first spreadsheet program, which is big number. So that would be one option. Then for the second one, we would still stay with mega. We would still stay with big word. But then for the second software, spreadsheet software, you would pick number world over here. So you can see this creates a different possibility. Then for the next one, since we're done with both big number and number world, that means we're done with big word also. So then from mega, you can move on to word world. So that would be your mega word world. And then, of course, you would have big number as the first spreadsheet software. So that takes care of this guy. And then the next one, you would have to do it with number world. So same word program, but now you have the second option for the number world. So does that kind of make sense of how you come up with these different combinations, different possibilities? So it's definitely a tedious process, right? Because you have to come up with that whole list, but the tree diagram makes it visually easier, because then you can say, okay, I'm done with this guy, which means I'm done with this guy. Now I can move on to the next one, and then, go ahead and create your other two combinations from here. So this would be with the big world. So still keeping the mega computer, but now, what was it? Great word. You are looking at great word as your third word software, or, word processing software. So great word for both of these. And then, of course, they would switch between the big number and the number world. And honestly, your next 6 options are going to be the same. The only difference is, instead of mega now, you will be using better byte. So you've basically taken care of, all 6 of these options that come up with from Mega World. And now you will repeat the same process, but this time, all of these will be better byte. So you would have your, and I'm just going to abbreviate it so we can save some time. So better byte with big word, with big number, Remember, in your homework, you will have to write out the full names. The abbreviations will not work. This guy will be Better Byte, big word, but instead this will be Number World as the Excel, equivalent. And same thing. So Better Byte, what was our second one? Word, world, and then again, big number. Better Byte, word, world, number world. And then Better Byte, what was after that? Great word. So great word, big number. And your very last one, Better Byte, great word, and then Number World. So literally same combinations as the first 6, but now your very first computer, Mega, gets switched with the Better Byte. But you can see these latter options match, what you had in these first 6 ways. So that's kind of how the tree diagram helps you out with creating the different possibilities. But then as far as just coming up with how many numbers you have, remember, this is where we multiply 2 times 3 times 2 to come up with the 12. And oh, looks like they did actually abbreviate it here. Interesting. So yeah, this is the different possibilities. So you can see how they are writing this using set notation. You've got your little, curly brackets over here. And then you've got option 1, comma, option 2, comma, option 3, and you list out all 12 of those possibilities. So that's kind of how your counting rule is working out. So question on this part over here, guys. So you do have a couple examples in your homework where they will ask you to find, what the count is, what the different possibilities are, but then also ask you to list out all the different options. So only a couple examples. So hopefully it shouldn't take you, too long on those, but I did want you to get a feel for what those examples might end up looking like. And you've got, references in here to look at some examples that can help you out. All right, very quickly, let's look at one more example. This is not with the tree diagram. This is more about the counting. So number 10 over here. Let's take a look at him. And this one is saying an audio equipment store has 10 different amplifiers, has 4 tuners, 6 turntables, 8 tape decks, 6 compact disc players, and 13 speakers. So they're saying, assuming that all components are compatible with each other, how many different complete stereo systems are available? So what do you think? How many different combinations do we have here? So like we normally do, just have your answer ready, and then you will send it to me in chat. So just do your calculation, type in your numbers, and when I ask you to, you can send your answer through the chat. Okay, so just get your answer ready. Couple more seconds. Okay, go ahead, send your answers in, guys. Okay, I'm seeing Logan, Brandon, Nidali, Ethan. Okay, Riley, Nicholas, Cynthia.
Oh, I forgot the 13.
Yeah, I was gonna say your number is definitely very small compared to the other, Cynthia. Yeah, so just like we did with the other examples, you just multiply all the different components we have over here, and that ends up giving you 10 times 4 times 6 times 8 times 6 again, and then times 13. And then you guys had 149,760. And that's a lot of possibilities of, coming up with different stereo systems. And you can see, guys, you have, different examples. Let me go ahead and save this and clear this out. So you can see a bunch of different examples here, which are kind of doing the same thing. They've got sporting goods store, a cafeteria with different dinner combinations, looks like a sandwich shop. So you can kind of see the theme. It's the same thing, how many different, and I love the sandwich shop examples because if you've ever gone to a Subway or whatever, there's always so many choices to choose from and you just never know what you're going to end up with. So it's just a good way to kind of see what different combinations you have. And I would say, next time you're in a Subway or any other kind of sandwich shop, see how many possible different combinations you can come up with. I think that would be a great idea to kind of look at some of this. All right, guys, so that's really the main part of section 2.3. I've got a couple more examples I'd like to show you. So we'll do that on Friday. We have different counting systems in section 2.4 where we'll do more on the permutation combinations. And that's pretty much it for chapter 2. And then we'll see how things go on Friday. If we can start chapter 3 on Friday, that'd be great. If not, we'll pick it up on Monday. So for now, I think your exam date is set up for Monday, the 27th, and I'm going to leave it there for now. But let's see how things go on Friday, and we may have to move it by a day, okay? But let's leave it for now and just start working on your homework if you haven't already, okay, guys? If you have any questions, stay back. If not, I will see you on Friday. All right, be careful, everybody. Take care. Stay safe. Yeah.
I
go
will
ahead.
be in class on Friday, just so you know.